Grab their coffee and find a seat. I'll make a few announcements. I'm Carlos Mila. If you don't know me, I'm the Center Director now at Stanford, and welcome to our CF Education Day. It's our 12th annual CF Education Day. Thanks to all of the team at Stanford. We had a very successful meeting year by year. And this is a very important time of the year for us because it's where we basically come to you as our partners in what we call the long path to getting to a cure of CF. And it's a good time for us to bring you up to date as to how close we are to that and how much we value your confidence in us in this, as we call it, partnership in the CF road. And as our mission statement very clearly says, one key component of our mission is to be partners with you in what we think is going to lead us to a cure for CF. So I have to thank the whole team at Stanford for helping us put this together, particularly to Colleen Dunn, who takes really a lot of the work on her shoulders to keep us focused on getting to this day. So thanks, Colleen, once again. And I also want to thank CFRI, which is this day taking us to the next level. We're streaming live, so I can start the conference by saying, live from Stanford, California. This is the CF Education Day. And without any further ado, I'd like to introduce our keynote speaker. We usually put a lot of thought when we go to a CF meeting as to what will be the most valuable thing to bring to you guys as the most advanced knowledge when it comes to CF. So it's a great pleasure to introduce to you Patrick Sosny, which is a junior faculty at Johns Hopkins, and I consider him a real rising star when it comes to CF. He's been kind enough to come all the way from Malaysia because he is someone that is so outstanding that he's keeping his foot on institutions that are on opposite sides of the globe. He's an assistant professor at Hopkins, and he's an assistant professor at Perdana University in Malaysia. And he's been kind enough to come and enlighten us on the work that is being done now to try to get a better understanding as to what CF mutations mean now that we're getting into an era where not just the cure for CF, but a better understanding of the genetic basis for CF is going to help us personalize medicine for CF patients. So, Patrick, if you'd be kind enough to...
Thanks, Carlos. Welcome, everybody. Welcome, everybody here, and welcome, everybody watching along on the web, wherever else. And thanks for the invitation. So I'm going to talk a little bit about cystic fibrosis mutations, cystic fibrosis genetics, and specifically in the framework of the research project that I've been working on with Gary Cutting, who's my primary mentor at Johns Hopkins, really trying to look at a wider range of cystic fibrosis mutations to characterize them well. So I want to talk about if we know cystic fibrosis mutations, if we know what mutations a patient has, how is that going to help us? How are we going to be able to use it to help make a diagnosis of cystic fibrosis, to be able to use the genetic testing that's being done to diagnose somebody with cystic fibrosis? And importantly, once we know someone has cystic fibrosis, I want to talk a little bit about some of the pros and cons of using someone's mutations as a way of telling how they're going to do, to predict how sick somebody with cystic fibrosis is going to be. And finally, and there's a lot of excitement about mutation-specific therapeutics, specifically the Vertex compound, ivacaftor or Kalydeco, that was recently approved for treatment of G551D mutations. I want to talk a little bit about how analyzing cystic fibrosis mutations is going to be important to choosing therapies in the future. And I think Dr. Moss is going to talk a lot more about that. So I'll kind of start with the low-impact stuff and let Dr. Moss bring it up to a higher level. So many of you know cystic fibrosis is a recessive disease, meaning you have to get an abnormal copy, a mutated copy of the CFTR gene, one from your mother, one from your father, to have the disease trait. So if two carriers have children, on average, 1 in 4 of those children will have cystic fibrosis. Half of the children will be carriers, and then another quarter of the children would be unaffected and not carry either CF mutated gene. About roughly 4% of Caucasians are carriers, and that depends a little bit on what particular population you look at. It also depends what you consider a carrier. What do you consider carrying a cystic fibrosis mutation? Because as I'm going to talk about, there are a lot of differences within the CFTR gene that we have a hard time telling, is this a cystic fibrosis causing mutation, or is this just an abnormality in the gene, a difference from what we consider the wild type of the normal pattern of the gene that isn't going to cause cystic fibrosis? So how do we make the diagnosis of cystic fibrosis? It's a kind of 1 from column A and a 1 from column B type thing. You need some evidence that the protein that the cystic fibrosis gene codes for, the cystic fibrosis transmembrane conductance regulator, one evidence that that protein doesn't work. You can meet that evidence by having a positive sweat test, by having another test that looks specifically at cystic fibrosis function, a nasal potential difference test where you take just a flexible catheter, put it up the nose, and take advantage of the fact that the cells in the nose actually are respiratory epithelium just like down in your lung, and they conduct chloride in the same defective way that your lung does up in the sinuses. And finally, you can make that diagnosis. You can meet that criteria for evidence of CFTR dysfunction by actually finding 2 cystic fibrosis mutations. Now, that's sort of one side of the equation. You also need a clinical scenario that's right for CF. So you need one of the cardinal clinical signs of cystic fibrosis, the pulmonary manifestations, the gastrointestinal manifestations, malnutrition or failure to thrive that we see sometimes in younger people, or obstructive azoospermia, infertility in males, that sometimes is the first thing that calls it to attention someone's cystic fibrosis mutation status. You can also meet something in that category B with a positive family history of cystic fibrosis. So if you have a positive sweat test and you have a brother or sister with cystic fibrosis, that's enough to make the diagnosis, or a positive newborn screen. Many, actually all states in the United States are doing newborn screening, and many of those start with a newborn screen test that looks at a biochemical test. Basically, it's a subtle test to look at how pancreatic function is working. So something from column A and something from column B. And the problem that I want to spend more time on and talk to you about is, what do we mean by 2 CF-causing mutations? Okay, so the CFTR gene, this is going to be review for many in the audience, but was identified in 1989 by positional cloning. So what we mean by positional cloning, and this is kind of interesting because it's one of the first genetic diseases that was identified in this way, is we took families where they knew CF ran in the family, and we're able to look at the portions of DNA, the portions of the genetic material that people in those families shared, and narrowed it down and narrowed it down and narrowed it down. And finally, we're able to narrow it down to a protein on chromosome 7 that codes for this chloride channel, a sort of a pore that sits in the membrane or lining of cells and helps regulate the chloride and fluid balance. CFTR is made up of about 170,000 nucleotides, individual base pairs, and it codes for 1,480 amino acids, the protein building blocks. So what do I mean when I say that? This is the cover of Science in 1989 when the gene was first cloned by a group at North Carolina in combination with the University of Michigan and the University of Toronto, Sick Kids Hospital at the University of Toronto. And this is Danny Bessette, the poster child that was on the cover of Science in 1989. This is him 20 years later. And this is a good bookend on where the disease is. I'm an adult cystic fibrosis physician, and it's encouraging that cystic fibrosis is becoming more and more an adult disease. It's a tribute to what our pediatric colleagues have taken good care of patients all along, that somebody like me can be doing CF. So what do I mean by mutation? And you're going to have to allow me a little bit of artistic license. And actually, usually this for the parents in the audience, this usually works. For the kids, the younger CF patients who don't know what encyclopedia is, they're used to Wikipedia. This may not go over so well. So I'm dating myself a little bit by going back to 6th grade when I was looking up in the World Book. But imagine we have an encyclopedia that's our genetic information. And instead of having 26 letters, let's just say we're going to have 23. We're going to have 23 volumes of that encyclopedia. The volumes of that encyclopedia would be our 23 individual chromosomes. And we don't have just, so it's not like you just have one A and one B and one C. You have 23 pairs. So in every cell of our body that has genetic information, we have sort of two sets of encyclopedias with 23 chromosomes. And those are kind of like the books or volumes within an encyclopedia. Now within that encyclopedia, there are little entries. So if you're in A, you can look up about Angola, and there's an entry about Angola. The entries within that encyclopedia are the genes. So you can sort of think about the encyclopedia. The genes are coded on a chromosome, and the A volume of the encyclopedia would have so many entries in it, just like for example, the 7th chromosome where CFTR lives is going to have so many genes that it codes for on that chromosome. And if you think about it, that entry, that Angola, is made up of a bunch of different words, and you put those words together into sentences. So that's that needle in the haystack looking at an encyclopedia. What we're looking for with cystic fibrosis mutations is a one-letter change that makes that whole entry on Angola not work. Obviously, the example doesn't work as well, because if there's one tiny misspelling, you're still going to get most of the information about Angola. But the genes may not work that way. You can have one letter that's substituted within a particular entry, within a particular gene, that's enough to cause the whole entry, the whole protein, not to work. So those are our 23 chromosomes, and the 23 chromosomes are made up of DNA, the essential material that codes for all the variability, what makes us different. The chromosomes are coiled up strands of this DNA, and these nucleotides are the individual bases that are the code of DNA, that are different, that provide the different letters that make up those encyclopedia entries. So these nucleotides, the backbone of DNA, are the individual letters, and those 3 individual letters that we call a codon code for, they basically tell the cell how to make proteins. When you break up those 3 letters one at a time, each of those 3 letters corresponds to a different amino acid. An amino acid is just it's basically what we make proteins out of. There are 20 amino acids, and we make proteins out of those 20 amino acids. So within the DNA, within our encyclopedia entries, there's a code for how we make every protein that our cells have in our body. And the proteins are really the action of the cell. They do what they need the cell. Now, there's a couple things about this that are remarkable, and you're going to have to allow me to geek out as a geneticist a little bit. Each of our cells contains every bit of information, but our lung cells just express the proteins that are important on being a lung cell. Our brain cells just express the proteins that are important to make it a brain cell. So there's a lot more going on than just the code there. There's a lot on the regulation of expression that may be a potential future target for ways not just to fix how the CFTR gene works, but fix how it's turned on. The other thing that I think is important to mention is if we think about our encyclopedia entries and think about our genes or encyclopedias, we have a lot more DNA than we have encyclopedia entries. It would be like you've got one page with Angola on it, but you've got hundreds of pages in between that have letters, but they don't make up an entry in that encyclopedia. So there's a lot more DNA on our chromosomes that actually codes for our genes. And we're just beginning to understand what that DNA, what we call the genetic deserts, what that's doing. But it seems to be involved in regulation, turning on the DNA, turning on the particular proteins we need for a lung cell to be a lung cell. Several different types of mutations, and I luckily saw Dr. Moss's slide, so I don't want to, he's going to speak about this much more eloquently than I will. But just to give a little bit of a frame of reference, there's several different types of mutations. We talk about missense mutations, where basically one of those amino acid building blocks is substituted for another one. So for example, the mutation G551D in CFTR. There's insertion deletions, where we might take a nucleotide in, put a nucleotide in, or take a nucleotide out. And one of the big problems with that is if you have those 3 reading frames, if you put an extra nucleotide in, it's going to change the reading frame so that the same 3 amino acid building blocks, those same 3 codons, aren't going to work in the same way. You're inserting another letter in, and it's going to change how everything looks. That usually is a deleterious or a particular substitution that's going to cause a problem. There are nonsense mutations that is another potential target for therapeutics, in which the particular substitution, the nucleotide that's replaced in the mutation, makes the protein stop sooner than it should be. So you don't make a full protein. And that because you've got a shortened piece of DNA that's coding for it, usually it doesn't make a protein at all. So those are likely to be deleterious or dysfunctional mutations. And there's something what we call splice mutations. So in between DNA and protein, there's a step called RNA. It's a way of the cell uses to make proteins. And that RNA is kind of cut and pasted together. If the cell doesn't cut and paste the RNA together, it can throw off the protein. And there are examples of mutations within CFTR that are splice mutations like that. So the hard part with this is that there's about 1,900 different variations in the CFTR gene that we know of. And this is well categorized by the folks at the University of Toronto and the CF mutation database that some of you guys may have come across, looking on the web about this. That's been the repository for genetic information about CF. We know so the common mutations, the delta F508 or F508del, G551D, R117H, the mutations that we see commonly, we have a good idea that they cause disease. We see them in enough patients. There are also some variants within the CFTR gene that we know don't cause disease because we see them commonly. But of those 1,900 different mutations in the CFTR gene, there's actually a large number of them we don't know what they do. We can't say for sure that just because you've got a genetic change there, that we know it causes cystic fibrosis. There are examples where you've got a particular genetic change, but it doesn't make the protein not work. So for example, you've got a letter that's substituted in your Angola entry, but it still makes the whole entry about Angola read the same. So for example, you can spell things the British way or you can spell things the American way. It would be that type of substitution. It's a substitution that doesn't mess up the protein or doesn't mess up the protein enough to cause cystic fibrosis. So that's really what my project, the clinical and functional translation of CFTR, CFTR2, is really to address this kind of gap in knowledge, to go from a few mutations that we know well to a bigger panel of mutations. So the cystic fibrosis mutation database that's run out of Toronto has been the repository for the genetic information, but we hope to supplement that with clinical information. So we hope to be able to provide not just all the different variants that are in the cystic fibrosis gene, but what those variants mean. What's the clinical consequence of having this particular mutation? Our two databases are going to be linked. So this is the information that we collected. So we were able to take information from the U.S. registry, the U.S. Cystic Fibrosis Registry, but also get information from other registries around the world. In Germany and Canada, they've got big national registries. And then in other parts of Europe where they may not have national registries, they have large clinical centers that keep databases. So by pooling all of that information together, we were able to assemble about 40,000 cystic fibrosis patients. We're able to look at what their CFTR genotype is, so what mutations they have. And we want to compare what mutations they have with how severe their disease is. So what their sweat chloride concentration is, the diagnostic test for cystic fibrosis, with what their lung function is, their FEV1% predicted, and with how their pancreas works, whether or not they have to take pancreatic replacement enzymes as a way to see kind of how that pancreas works. So how can we tell if a particular nucleotide change, a particular amino acid substitution causes disease or not? So if we have a letter change in that gene, how do we know if it causes cystic fibrosis or not? The first thing I would ask is it a clinically consistent mutation? So if I have a patient that has this particular DNA variation, does that patient have the clinical symptoms of cystic fibrosis? Now remember, you need two copies, so we have to be able to interpret one mutation and the other. But let's say we have a delta F508 on one chromosome, so we know that that's a disease-causing mutation, and we have an unknown mutation on the other chromosome. It's easy for me as an adult physician to be able to look at that patient and say, oh, have you developed obstructive lung disease? Do you have an abnormal sweat chloride? That becomes much tougher when you have a newborn or a young child that might not have time to develop symptoms yet. So clinical criteria is probably not enough because we'd like to be able to tell based on the mutations themselves. So one of the things we do also is to take the mutations and study them in experimental cells. Basically look at how this protein with this particular amino acid change or this particular nucleotide substitution, look at it in a cell and see, does it work like normal CFTR? Does it conduct chloride? Does it regulate the airway surface liquid the way an epithelial cell needs to have its airway surface liquid? Study that particular mutation in an experimental cell to see, does it behave like a CF mutation or does it behave like a healthy CFTR gene, or healthy, or what I may slip in and use the genetic term wild type, meaning it's the type that we see more in nature. But finally, just because we have a particular nucleotide change or a particular amino acid substitution, we also want to know that patients that have that mutation, that have that nucleotide change, have cystic fibrosis, and there are no patients that have that particular nucleotide chain that don't have cystic fibrosis. So ideally, we'd have everybody's genotype. We know the cystic fibrosis status of everybody in the world to be able to say, CF patients have this mutation, and none of the people that don't have CF have this mutation. And I'll talk about some of the perils and pitfalls where we've been wrong based on clinical or based on functional information. And we needed to use population or genetic information. So if we meet all these criteria, that's enough to say that this is a mutation that definitely causes cystic fibrosis. So what we've done is, in addition to doing research on this, we've put this in a website that's going to be publicly available hopefully soon. This is a website that will be geared both towards scientists and clinicians studying cystic fibrosis, but also to the general public. So you can see that you can sort of enter the website in one of two ways. There's a way to enter specifically, excuse me, for patients and family members, and there's a way to enter, for the more sophisticated CF researchers, CF clinicians. Both sides will be open to the public. So as the public can look over on the scientific side and vice versa. We're not trying to keep any data away from the public, but the language specifically, might make more sense on one side versus the other. So, for example, for G551D, that from just a very simple point of view, we're going to provide the information that, based on what we know studying this, and based on what's been published previously by other researchers, that we know G551D is a disease-causing mutation. It's not a neutral variant or a particular amino or a particular genetic change in the CFTR gene that's not associated with cystic fibrosis. But we're going to provide more detail than just that. And we'll actually be able to look at the breakdown of what patients with G551D look like compared to just average CF patients in our CFTR2 database. So compare their sweat chloride concentration, compare their lung function, compare how many of the patients have pancreatic insufficiency or need to take pancreatic replacement enzymes, how many patients culture Pseudomonas, and what the average age is of the patients we're looking at. And the age is important because it helps us to interpret kind of everything else. So the important thing that you'll notice here, especially about the lung function, is that we're showing the range. And the range for this is pretty wide. So we hope that this is going to be a better resource to determine for a given cystic fibrosis mutation, number one, does it cause CF or does it not cause CF? There's 1,900 mutations. There's a lot of mutations to get to. But many of those mutations are just seen in 1 or 2 people in the world. So we hope we're starting with the mutations that are seen in the most people, at least seen in 5 to 10 people. But in genetics, in medicine, in biology, there is no black and white. There's no absolutes in doing this. And there are many examples where we've been, in the past, where researchers have been wrong in thinking a particular mutation causes CF or doesn't cause CF. So allow me to kind of talk about one of the reasons why we need to be so careful with this. So I148T. We originally thought, researchers in cystic fibrosis originally thought the mutation I148T itself caused disease. Genzyme, a large genetic testing company, noticed that they were doing carrier screening. So they were screening individuals that were thinking about having children. And Elizabeth Rolfe, the PhD, one of the directors of Genzyme, actually noticed that they found a lot of patients that they were screening as carriers. So these are healthy people that are considering having children, and they have CF carrier screening, had a mutation like Delta F508 on one chromosome, and they actually had I148T on the other chromosome. And these are people that were coming in for carrier screening. So this is a mutation that we suspected was CF causing, But the folks at Genzyme, actually the genetic testing lab, noticed that, wow, a lot of the people that we think are getting just a healthy screen actually have this mutation. And when we investigated further, so we put that mutation, researchers studied that mutation in cells, they actually found that when they studied it in detail, that it worked more like a normal, healthy, or wild-type cystic fibrosis gene. It didn't work like a mutated gene like delta F508 or like G551D. And that led them to do further genetic testing on the patients that they suspected had cystic fibrosis from I148T, and they actually found another mutation. And they found a mutation in a place they weren't looking for mutations previously. So they found this 3199 deletion 6. So they found a mutation that all of the patients that had I148T that had cystic fibrosis have. So in other words, the I148T was sort of a red herring. It was a marker that that 3199 mutation might be there. There were other patients with just I148T on their own that didn't have cystic fibrosis. This was, so for years, people were saying I148T is a disease-causing mutation. And actually, I148T was just what we call a complex allele, where there are two genetic changes on the same CFTR chromosome within the same CFTR gene. So the other headache mutation is R117H. This is a mutation that genetic counselors typically have a more challenging time explaining. And it's a sort of similar story. This is about the third or fifth most common cystic fibrosis mutation. So it's a mutation we commonly see in CF patients. So this was researchers that noticed, actually. This is researchers looking at a database of patients actually in Northern California. Kaiser Permanente was looking at patients, and they were doing genetic testing, and they found, thank you. I'm going to spill it on my shirt, and that's even worse than coughing. So R117H was seen commonly, and when they looked at a broad group of healthy individuals, they actually found people similarly that had one mutation that we know causes CF, like delta F508, and had R117H on the other chromosome. And if this is a disease-causing mutation, why did we have these healthy people that had R117H and delta F508? And the further investigations revealed that R117H on its own didn't cause cystic fibrosis. It needed to be present on the same CFTR gene with another genetic change, another subtle genetic change, a change in what we call the polythymidine track that helps control how well CFTR is spliced. So that people that have R117H with this 5T variant are people that are more likely to get cystic fibrosis. People that have R117H with the 7T variant, so another flavor of R117H, were less likely to have cystic fibrosis, although there actually are a few people with that 7T variant that do have CF. So these are two examples where the best and brightest, where the CF research community that studies this well was actually wrong. It's one of the reasons why we're going through the stepwise process of looking at the clinical information, looking at functional information, and also looking at the population mutation. And these are both examples where we really needed population data to be able to tell us if these mutations caused CF or didn't cause CF. So now that we know that which mutations cause CF, the important question everybody wants to know, what me as a CF clinician wants to know, if I know my patient's mutations, can I predict how they're going to do? And the scientific term that we're going to use for that is the genotype, or the particular genetic changes someone has, phenotype, the manifestation of those genetic changes interaction. So looking at the genotype-phenotype interactions with cystic fibrosis, or as a way to try to tell, based on what mutations you have, how you're going to do. How long somebody's going to live, what their lung function is going to be, whether or not they're going to have to take pancreatic enzymes. So this is I always show this slide. These are twins that we followed, and these are actually identical twins. So they have the exact same CFTR mutations, and they have the exact same, all their other genes, so all the other potential modifiers. These are identical twins that share 100% genetic similarity. So this is their FEV1, the breathing test that many of you have done in clinic. This is their FEV1 over time. So 1 is 100% predicted. And you can see that they kind of, vary around as they get older, as, their lung function goes down a little bit. But you can see right here, there's a big difference between one of the twins and the other twins. And this is right around the time that they went to college. These two twins went to different colleges, and one was pretty good about keeping up with his medications, about keeping up with his clinic appointments. And another child just, actually got busy with school, not trying to be a bad kid, but wasn't as good about taking mutations, didn't do everything, and just probably had bad luck as well. And you can see their lung function's really divided. So even though they've got the same mutations, you can see a big difference in the lung function. And actually, twin A, the sicker twin, actually went on to needing a lung transplant. So this is something that Dr. Moss is going to talk a little bit more about. But we use the mutation class system to help us characterize how severe a CF mutation is. You're going to see a lot in the literature, and if you read on the internet about cystic fibrosis, you may hear a mutation characterized as a severe CF mutation or a mild CF mutation. And I may even use those terms here, but I really don't like those terms because I have a lot of patients in my adult clinic that have mild mutations that have severe lung disease. It might be that they have that lung disease later in life, but they're still bothered by it. They still need to be in the hospital getting IV antibiotics. They still need, all the care that people with the, quote, severe CF mutation. So I'd really like to avoid that because, as I'm going to show you throughout the course of this talk, the genetics are only so good at predicting how we're going to do. But if we break down this is sort of I'm going to date myself again, but the Schoolhouse Rock, I'm just a bill. And you hear how a bill goes from, initial idea to becoming a law. This crude diagram here is sort of how CFTR goes from genetic information in the nucleus, or the part of the cell that stores our genetic information, our chromosomes, and goes up through to eventually become the protein that acts on the top or the apical surface of cells to help regulate the fluid and electrolyte balance of that cell. So this could be a lung cell, this could be a pancreas cell, this could be any cell where we have CFTR. And different mutations cause the CFTR protein to sort of stop at different places along that progression from genetic material in the nucleus to a protein that's working on the cell. And classes 1, 2, and 3 are typically mutations that are characterized as class 1, 2, 3 are typically mutations that cause the protein to not work earlier. So they either cause no RNA expressions, and this is an example of this would be like those nonsense mutations I talked about, or they cause the CFTR protein to not fold correctly, not assemble itself correctly from just a string of amino acids into the protein that it needs to be. Delta F508 is an example of a class 2 mutation, or it could be a mutation that doesn't get, the channel can't get turned on. So it forms a chloride channel, it might even get to the apical or top surface of the cell, but it can't be turned on. So it doesn't, it's not able to be activated, it's not able to connect chloride. And G551D is an example of that. If we look at those class 1, class 2, and class 3 mutations, typically those mutations are associated with pancreatic insufficient disease. So patients with at least one copy of class 1, 2, or 3 mutations typically have to take pancreatic replacement enzymes. Remember what I said, there's no absolutes in medicine, and there are plenty of patients that have these class 1, 2, and 3 mutations, that have 2 copies of these class 1, 2, 3 mutations, that actually are able to not need pancreatic enzyme replacements. So it's not absolute. Class 4 and class 5 mutations are both types of mutations that are associated with some CFTR getting to the apical surface, the top surface of the cell, and it's able to conduct chloride a little bit. It's able to do a little bit of what it needs to do. Class 4 and class 5 mutations like R17H or 3849 minus 10 kb C to T. These mutations in class 4 or 5 have a little bit of residual CFTR function. So the protein works just a little bit. And because that protein works a little bit, they're less likely to need pancreatic enzyme replacements. Now, that's what we're taught in textbooks. We're taught that if you have one copy of class 4 and 5, that you're likely to be pancreatic sufficient and not need pancreatic enzyme replacements. As an adult doctor, I have a lot of patients that over time, even though they have class 4 and 5, or what we consider the words that I don't like, the milder mutations, over time their pancreas just stops working. Many of these patients with class 4 and 5 mutation might not need to take pancreatic enzyme replacements, but they might be more likely to get pancreatitis or inflammation in the pancreas, which subsequently can lead them to need to take pancreatic enzyme replacements. So CFTR genotype has been useful to be able to predict if someone's going to need to take pancreatic enzyme replacement or not, but it's not absolute. It requires that you know whether a mutation's a class 1, 2, or 3 mutation or a class 4 or 5 mutation. And there's a lot of subtleties. If we, looked at a number of different mutations, it would depend what cell type you examine that mutation in to tell whether it's a class 2 or class 4, for example. There are some examples where this is not black and white, and we can't clearly put all of those mutations in the box. But the functional testing that we've done as part of the CFTR2 project at least gives us a clue as to what type of mutations this is going to be. So there are many problems with that. And it requires, the biggest problem requires that we have to, if someone has a novel mutation that we've never seen before, we obviously don't know what class of mutation it is. So it's hard to be able to predict what pancreatic function that patient's going to be. All right, so I'm Baltimore, I'm from Hopkins, so we're going to do some Baltimore examples to kind of bring this to life, okay? So somebody always raises their hand when I show this and say, the Utz girl is not from Baltimore, the Utz girl is actually from Hanover, Pennsylvania, but it's close enough to Baltimore, so you'll have to bear with me. So we've got the Utz girl, and her genotype is Delta F508, so she's got one copy of Delta F508 from mom, one copy of Delta F508 or F508 del from dad. We've got Edgar Allan Poe down here, who actually just died in Baltimore. He wasn't really from Baltimore. And he's got one copy of Delta F508, and he's got another copy of 3849 plus 10 kb C to T, a mutation that's a splice-type mutation. We've got Omar from The Wire. I don't know if you Obama recently said that his favorite character on The Wire was Omar, which if you've watched The Wire, obviously your favorite character is Omar. But so Omar many of the patients have been diagnosed with cystic fibrosis and might have some of the genetic testing done. But actually, even patients that have had genetic testing done, sometimes we don't know what the other mutation is. So if a patient's sitting in front of us and we say, wow, they've got an abnormal sweat chloride, and they've got lung disease, and they've got pancreatic disease, and even though we can't find that second CFTR mutation, sure looks like cystic fibrosis. They've got one mutation. This is a patient that we'll call CF. So there's plenty of patients around that aren't completely genotyped. So Omar's got Delta F508 and unknown. And finally, we got the Natty Boh guy. It's a big sign in Baltimore. It's a beer that they hardly make anymore, but a big sign in Baltimore that's still there where the brewery is that winks every 15 minutes or so. The Natty Boh guy, kind of iconic, sort of the Pabst Blue Ribbon of Baltimore. And Natty Boh's got A455E and R117H. So he's got those two mutations. So let's sort of use our rules to kind of predict how they're going to do. So we would expect that the Utz girl that's got two copies of Delta F508 is going to be pancreatic insufficient from birth. She's got two of those, I don't like the word, but two of those severe mutations that aren't really associated with any residual CFTR function. And the Utz girl, it's pretty safe to say that it's likely she'll be pancreatic insufficient from birth and need to take pancreatic enzyme replacements. So interestingly, that's what we have in the United States, where 99.7% of patients with Delta F508 are pancreatic insufficient from birth. If you go to Israel and you have patients that are Delta F508, only about 90% of those patients actually need pancreatic enzyme replacement from birth. So despite the fact that they have the exact same genes, patients in Israel are less likely to need pancreatic enzyme replacements. That could be something about the physicians. We're just more likely to prescribe pancreatic enzyme replacement. That could be something about the diet. It could be something about other genetic changes they have that are outside of cystic fibrosis that make them more or less likely to have pancreatic insufficiency. So Omar, Delta F508, but the other mutation is unknown. So we really don't know if he's going to be pancreatic insufficient or pancreatic sufficient. Edgar Allan Poe, who's got one copy of Delta F508 and another copy of a splice mutation, a class 5 mutation that, remember the cut and pasting of putting the protein together, those mutations usually are associated with some residual CFTR function. So it's likely Edgar Allan Poe is going to be pancreatic sufficient, not need pancreatic enzyme replacements. But as he grows older and as he gets to the adult clinic, it's more likely that he may need pancreatic enzymes in the future. So probably PS as a child, but might need them as an adult. And finally, we've got the Natty Boh guy, who's got two copies of those class 4 or 5 mutations. A455E is a class 4 mutation, and R117Hs as well. So he's got 2 copies of those mutations that have some residual CFTR function. And it's likely the natty bow guy is going to be pancreatic sufficient. And it's also possible with those 2 mutations that he might have a milder course. He's got 2 mild mutations, so it's reasonable to expect that his disease might be more mild. But can we predict lung function for any of these patients? We can't. We really, really can't. I'm going to show some data where we're going to try to do it, but there's no way looking at a child, even if we do the state-of-the-art genotyping, to be able to say this is what their lung function is going to be. There's no way of predicting because there's too big of a spread. So let me show this. Right, this is my one science slide. So what I want to show with this is on this axis here. I'm showing, and this room probably understands this better than I do. I'm used to presenting in Baltimore where we have a wide spectrum. We have very, very well-educated patients and patients who are not as well-educated. So this is, I'm probably going too slow for this room here. But on this x-axis, we've got CFTR function. So when we look at CFTR, how well it conducts chloride. And if this, I'm just going to point out this, 100 point here. You'll notice this is a log scale. But 100 means it conducts chloride 100% of what wild-type CFTR conducts chloride. So it conducts chloride as well as a copy of CFTR that doesn't have any mutations in it. So down here would be mutations that really mess up the protein, and it doesn't conduct chloride at all. And as we go this way are going to be mutations that work better, that have residual CFTR function. And if we look on this axis, what we do is, so each of these dots represent an individual mutation. On this axis is the patients in our CFTR2 database, what their lung function is, what their FEV1% predicted is. So 100% predicted down to 0%. So each of these dots represents a mutation, the combination of what its function is and what the average lung function is for patients that have it. So for example, mutations like delta F508 or F508del are going to be down on this end of the spectrum. Not much residual CFTR function at all. Mutations like R117H are going to be on this end of the spectrum. There is some residual CFTR function associated with R117H. But if you look at this, there's not a huge difference. So a couple points. The relative difference between our R117H patients and our delta F508 patients is actually pretty small. You compare on this line, it's only maybe 5 to 10 percentage points of FEV1 different. And that 5 to 10 percentage points of FEV1, for those of you that do PFTs, it could be, oh, I had a good day, oh, I had a bad day. You might not necessarily even do anything with a 5 to 10 percentage point difference. Sometimes it's very clinically significant, but it might be something you just say, oh, I feel pretty good. PFTs are just a little bit down. It's within the variance that we see. The other thing about this that makes it difficult to interpret is this is just one point in time. And what we want to know is not just what someone's lung function is at one point in time. We want to know what their lung function is longitudinally. And we want to look at how their lung function declines over time. So it's less statistically valid because if we have all these patients here that are R117H and they have an average FEV1 of, let's say, let's just call it about 78% predicted. And we've got the patients with delta F508 here and they've got an average FEV1 of, let's say, about 70% predicted. So it's an 8-point difference. But what if I told you these patients with delta F508, their average age is 15, and these patients with R17, their average age is 40? There's a difference between a 40-year-old with an FEV1 of, say, 50% predicted and a 10-year-old with an FEV1 of 50% predicted. And that's why to some extent, it's not fair to make these comparisons. The other thing that you'll notice is there's pretty wide error bars with this. There's a wide range. There are delta F508 patients that have very, very severe lung disease. There are delta F508 homozygous patients that have 100% FEV1. There are delta F508 patients that are in their 30s with 100% FEV1. So there's a wide range of what someone's lung function can be. And all of these things are problematic. I would love to know from genetic testing at birth, when we get genetic testing back, I'd love to be able to know this is what someone's lung function is going to be. I'd love to be able to tell family members that. But there's too many other variables that contribute to lung function. But what does this relationship mean? And I want to at least spend a little bit of time talking about the fact that this is on a log scale. So going from here to here, it's actually a logarithmic improvement. This is typical of a disease like cystic fibrosis that's a recessive disease. we're using the CFTR function as a way of defining how bad a CF mutation is. And the chloride conductance that we used as a way of defining CFTR function is only one way to define how bad a CF mutation is. And actually, Professor Jeff Wine, who's here, has done a lot of work looking, for example, not just at how cystic fibrosis conducts chloride in epithelial cells, but how it works actually in the mucus gland. And maybe me studying an epithelial cell isn't really what's important. Maybe it's more important to study it actually in the glands. So we might not be capturing how severe a mutation is just by looking at what I'm calling its CFTR function, because there's a lot of different ways you can potentially interpret that CFTR function. There's great variability in this. And CFTR function, as I mentioned in that last slide, it plays less of a role. I'm better able to tell you if you're going to be pancreatic sufficient or insufficient, although that's not perfect. We're a little bit better able to say what someone's sweat chloride is going to be if we know their genetic mutation, even though most patients get their sweat chloride back before they get their genetics back. It's a little bit easier to say because that's more proximal to where CFTR is going wrong. And there's a lot of other variables. So even in a Mendelian disease like cystic fibrosis, where we know we've got a gene that causes the disease and the disease affects the lungs, even if we know what those mutations are, it's very hard to predict what the lung function is going to be. The genetics term for this is lung disease is a complex trait. And it's going to make it, this is one of the challenges, the hurdles of individualized medicine. So if we know all of our genetic changes, can we predict what our cholesterol is going to be, whether or not we're going to have a heart attack, whether or not we're going to develop Alzheimer's disease? The problem with that is, for example, in lung function, that we know cystic fibrosis, the CFTR gene is tremendously important for. Even in lung function, in CF patients, it's difficult to interpret to go from what the CFTR mutation is to predicting what the lung function is going to be. This is one of the challenges of enacting the personalized medicine revolution that everyone's talking about. The silver lining in this is that now we're just on the brink of therapies that have the potential, and Dr. Moss is going to speak about those, of therapies that have the ability to fix CFTR, to fix what it's doing. So to essentially, if I look at this graph, to go from here, where you're at almost zero function, to here. That's the hope that these therapeutics will increase CFTR function. And given that that's a log scale, a little bit of change in function is going to go a long way. So those patients with very, very low CFTR function, like G551D, got a lot of benefit from the augmentation in CFTR function that was seen in that clinical trial. A little bit of restored function is going to go a long way. You're going to ask me, how much is enough? Consultants want to know how much CFTR function is enough. And the problem with saying how much CFTR function is enough is all of those things we talked about with the variability of lung disease. Because those error bars are big, I can't draw a line on this graph to say this is how much we have to fix CFTR to have someone be healthy. Because it's going to be different for every individual. Dr. Moss will talk a little about, you guys have all heard about Kalydeco, ivacaftor, the new Vertex 770 drug, just for patients with G551D mutation, about 4% of the CF population, but dramatic changes in lung disease, dramatic changes in weight, and decreased pulmonary exacerbations, very encouraging, and it helps really to prove that a mutation that in cells we know it improves CFTR function. It's encouraging to see patients get better. So we knew it fixed the CFTR in cells. It's very encouraging, even in a short-term trial. This is the 28-day, and they also published the 1-year trial. Even in those patients that had that, it's very, very encouraging. But unfortunately, G551D is not everybody. We need more drugs like this. So the question I get asked more than anything else is, are there other mutations? You've looked at all these other mutations. Are there other mutations that ivacaftor is going to be useful for? And the way the FDA ruled on this was that ivacaftor is just approved for G551D. There are other mutations that behave like G551D that actually Vertex is beginning to do clinical trials for. And you contact your CF doctors, they'll let you know, because Vertex is actively looking for patients with those mutations. The problem is it's a lot of very rare mutations. G551D is in about 4% of the population. The other gating mutations that they're looking for are all just seen in 10 to 20 people in the United States. So it's a very small pool. And it's very hard to do a clinical trial to approve a drug for the FDA if there's only 10 people in the world with that mutation. The functional testing that we've done for CFTR2 is going to be a way to, the functional testing we've done for CFTR2 is going to be a way to analyze, these mutations to know kind of how much we need to fix them and to know what therapies they're going to be amenable to. So now that we're putting all this information in one place, I would envision, and it's there for G5-1D, but I'd like more drugs. I would envision this is, what the average lung function is. This is what the average pancreatic function is. This is what we learned from functional testing of the mutation. This is what drugs you're eligible for with that mutation. And that's the hope, the pharmacogenetics hope for what CFTR2 is going to do. We need more drugs for it. So summarizing this, there are a lot of mutations in the CFTR gene. Hopefully our CFTR2 project and the website for this is going to better define which ones cause CF and which ones don't. For an individual patient, though, it's very, very hard to tell because there's so much variability. So the CFTR mutations may be helpful in predicting someone's pancreatic function, but it's going to be much tougher to be able to predict what their lung function is going to be. And that lung function is the biggest determiner of morbidity and mortality, how long somebody's going to live, what their quality of life is going to be. As these new therapies become available, hopefully our CFTR2 is a resource for patients to go to, for researchers to go to look at, is this a mutation that may be eligible for this particular type of therapy? And this is going to dovetail well with what Dr. Moss is going to talk about with some other promising mutation-specific therapeutics. Some take-home points that, if you remember this, if you haven't been genotyped, get genotyped. Actually, the foundation will pay for you to get genotyped now. So if you're a Delta F508, your family member is a Delta F508 unknown, actually the CF Foundation will pay for that. Actually, Vertex is footing the bill. It's probably not publicly known, but they're looking for more people they can give their drug to, so that's okay with me. It's an aid in diagnosis, but there are no absolutes. We can't predict how severe somebody's lung disease is going to be, but CF, really the reason to get genotyped is in the future, it's going to be a way to tailor therapy. There's tremendous variability on the individual level. A lot of people I thank. This is kind of our CFTR2 team. This is Gary Cutting, my boss, that runs the whole thing, but this is an international team. Italy, Toronto, the folks that run the CF mutation database, and then Chris Penland at the CF Foundation. And I will point out that the Cystic Fibrosis Foundation funded this work. I get grant support from the Cystic Fibrosis Foundation, so it's a conflict of interest. If anything, I want to diagnose everybody with cystic fibrosis, especially people that, that want to give generous gifts to the CF Foundation. Vertex Pharmaceuticals actually performed a lot of the functional testing for us. So they did a lot of the lab-based testing because they want to look for more mutations that they can give their drugs to. But they've been important scientific collaborators in this process as well. These are other kind of people on the CFTR2. www.cftr2.org. It will be online soon. It's not yet. And one of the reasons it's not yet is we want to get this right. The website is put together. It's, it's all there. The information's all there. But we want to make sure this is right. So we're having really experts around the world analyze CFTR2, analyze what's there now to make sure when we open it up to patients, we don't have mistakes there, and we don't have information that may potentially be misleading or information on the website that may particularly give you either false hope or a bad impression of how somebody's going to be. Remember, there are big ranges in all of this, and there's no way looking at what everybody else does how your individual child or your individual family member is going to do with that. So that's kind of the most important caveat I can give. All the CF patients I've talked to know this, and they want the information. That I'm willing to look at the wide range, and I don't want to stand up here and be paternalistic and say we want to make sure you don't misinterpret that the wrong way. But that's going to be an important part about a wide range of people looking at this, and not just people with cystic fibrosis, people that potentially are getting carrier screening too and making reproductive decisions based on this information. So I'm happy to take any questions. Yes. If I gotta be on the web, you gotta be on the web.
Okay. I had an I have a question about implications of insurers reading this information, and I've just been battling insurance companies for the last, especially the last 6 months.
Yeah,
just for one drug that's a standard drug, it's a lot of money. But
yeah.
so what happens when your child gets genotyped and then they go to the insurers use this information for their purposes?
So I can tell you the fairy tale Lake Wobegon answer, and I can tell you the real life answer. The fairy tale Lake Wobegon answer, where everybody's above average, is that so in 2007, the Congress passed the Genetic Information Non-Discrimination Act, or GINA. And actually, interestingly, it's really the only bill Obama authored as a senator. Most of the time, he was a senator. He was running for president. But he was involved he actually was involved in this legislation. He's one of the co-authors of this bill. So the Genetic Information Non-Discrimination Act says that an insurance company can't discriminate against you on the basis of genetic information. They can't deny health care coverage to you. And this is even pre-Obamacare, denying for, the pre-existing condition going away. So an insurance company can't deny for genetic information. So in theory, someone that has genetic testing done and they find a CF mutation, or maybe they find a CF variant that's not associated with cystic fibrosis, but what we call a mutation of varying clinical significance, or a mutation that sometimes causes CF but sometimes doesn't. In theory, insurance companies can't deny that. And the hard part is, what do you consider genetic information? So if I've got a family history of heart disease that runs in my family, well, that's sort of genetic information. And it becomes much harder to kind of draw the line from that. So I don't know how this is necessarily going to play out. But in theory, and I think GINA is in place. The worry in the genetics community is that it's not going to hold up in court. That they're not going to be able to, if someone sues for an insurance company denying coverage, or an employer not hiring somebody because they have this particular mutation, there's a worry that there's going to be legal loopholes around it that's going to allow that insurance company or that employer to get around it. So unfortunately, the real world is I don't know. But there's a law in place, and there's actually a good law, and it's important because we're starting to look at genetic testing for a lot of different things, for common things, like asthma, like susceptibility for heart disease, like susceptibility for diabetes, diseases that run commonly in the population. And if we all have genetic variations, we all have mutations. I want to get away from using mutation as a kind of a bad word or an X-Man word, because a mutation is really, from a geneticist point of view, it's just a change in DNA. And we don't know the functional consequence of that. So we all have mutations. It's a question of, do you have the perfect storm of mutations and environment and luck that give you a disease? So it's I think it's a messy reality. I'm going to let the mic people pick.
Hi, I'm curious about the mismatch between genotype and phenotype that you talk about, specifically those of us who have a severe mutation and not advanced disease, and what's going on?
So it could be a lot of things. Of course, it's great care that you've gotten here at Stanford. That's the most important thing. But even people with great care do. So it's a combination of potentially care, potentially the fact that as we've been recognizing this disease earlier, we paid more attention to nutrition. The therapeutic options that have been around are helping to keep things. All the advances that have been made in cystic fibrosis add up to that. It's probably to some extent other modifier genes. So there's other genes that we don't understand how they work that are protective in doing that. But we can't always understand what makes people with, I want to get away with people with class 1, 2, and 3 mutations have milder disease, and people with class 4 and 5 mutations have severe disease. That's there's an element of chance of luck in all this too. But it's also you taking care of yourself and your doctors and nurses, and nutritionists and physical therapists taking good care of you.
They're doing more screening now for infants, and how is that impacting the databases for CFTR1 and 2?
So more people know their genetic information. So not all states. So I come from Maryland, that does the cheapest possible screening they can do and doesn't do DNA testing. But it's useful because for more newborns coming into the clinic, we know what their genetics are right away. We know what their genotype is right away. California, that's doing actually pretty progressive and pretty. They're doing genetic testing, even not just for the mutations we know cause CF. They're looking for all variants in the CFTR gene. So California has the useful thing of being able to follow somebody with some of these mutations we don't know about. Some of these mutations we just haven't seen them in enough patients, or the functional testing is kind of equivocal, or some patients we find with the mutation have CF, but other patients don't have CF. So California is going to be a great repository for those patients that we don't know what it's going to evolve into. Maybe it's healthy as a child and they develop obstructive lung disease in their 50s and 60s. That's still something I think we'd want to know about. So it's helping that we know genotype early. Take maybe one more question, and I don't want to get the whole day behind.
If one sibling has the F508 and the other two siblings are healthy, will they be carrying the healthy ones? Be carrying the F508, or can there be a mutation?
They have basically they have a 50% chance, counselor, and having them go through
a different mutation of what the one sibling has.
They likely would have the same gene. With that said, there are instances where there's sometimes a couple different flavors of Delta F508, one of the cells, but generally they would have the Delta F508. So it would be something to that you know what you're looking for if you're doing genetics. So I just want to once again, it's because of the people at Hopkins. Mike Boyle's the adult director there, and it's because of the entire team. And I after finishing residency and doing fellowship and thinking about what I wanted to do, there's a lot of things in pulmonary medicine that seemed exciting, but the reason I did CF is because they took great care of people and had fun. And getting to see Dr. Milla and the rest of the Stanford team, Dr. Moss, that you guys have that too. You're lucky to have that too. So that's this is a great CF team. It's great to be able to be here and speak to you. Thanks.
Thank you, Patrick. That was wonderful and quite enlightening. I've learned a lot today. To follow and to dovetail nicely with all of the genetic information, we'll have Dr. Moss, who I think no one better than him to tell us about the updates on where we're going with CF therapies. He's been on the front line of finding the cure for CF for all of his career. So, Rick.
Thanks, Carlos.
There's seats on the front.
Okay. You may have noticed during Dr. Sazne's talk that the arrow doesn't work on the big screen. So if it's absolutely necessary, I might walk out in front and use the pointer, but otherwise it won't be available. It's the advanced technology up here at the podium. So I'm going to be talking about some of the recent drug trials, and the preceding talk really has provided a great introduction to that. Let's start by just considering where we stand today in terms of how we treat at least the lung disease in CF, and this is a kind of overview of the different kinds of therapies that we have available. So everything in the blue box represents a point of attack on a problem clinically in CF. So, for example, if you have problems with obstruction and wheezing, you can get a bronchodilator like albuterol. Since your airway secretions are dried out, we might give you hypertonic saline or mucomist. If you have thick, sticky mucus, we might give you pulmozyme, and so on and so forth. But you'll notice that all of these current therapies are aimed at what we might call secondary problems in cystic fibrosis that are represented in the bottom two-thirds of the slide there. So the basic problems of infection, obstruction, and inflammation, they're not the root cause of the disease, they're the result of the disease. And a lot of the difficulties that Dr. Sazne talked about in terms of predicting somebody's lung function really have to do with the evolution of these secondary problems. So, for example, if you're unlucky enough to get a respiratory syncytial virus infection as an infant, that's going to could affect the whole course of your lung disease, where someone with the same genetics might not get that infection and might have a different course. So what I'm going to be emphasizing is at the top of this slide, and you can see here that there are three ways that we can think about fundamental treatment of CF, and the first involves something that everyone in the room is familiar with, the idea of gene therapy. So we would basically replace the bad CF gene with a good CF gene. This is something we were very hopeful about 15 or 20 years ago, and we've learned a lot about the fact that we know less about how the body defends itself against foreign genetic material now than we did 15 or 20 years ago. It's a very difficult task. There is a project in the United Kingdom looking at this kind of therapy, nothing really active in the United States at this point. So I'm not going to talk any further about that. The defective CFTR protein you've heard a lot about, and this is going to be something I'm going to emphasize, but I also want to mention that a third way to attack this problem that doesn't depend on the genotype or the CF protein per se, but rather on its function, would be to give some kind of drug that could improve the fluid and water function of the respiratory epithelium. And unfortunately, we don't have a good answer there, although there's very active research, including clinical trials, that some of you have been involved with looking at that aspect. So what I'm really going to be talking about is this central panel here of defective CFTR protein. You can see that there are a number of drugs listed there, all of which are in clinical trials now. So it's very encouraging to realize that we moved from the bench to the bedside on this. So to set the background, you've heard a lot about the production of CFTR protein from the gene. Let's remember that the CFTR gene regulates salt transport, but there's really a three-stage process involved. We start in the nucleus of the cell, so the DNA has to go ahead and have this translated from DNA into a protein, and that involves the messenger RNA that was briefly mentioned, and other proteins that translate the genetic information into a protein. This takes place in a specific area in the cell called the ER, or endoplasmic reticulum, and it's finished up in another place in the cell called the Golgi apparatus. And once all that is done, then you have a fully made and packaged protein that can then go to where it's supposed to function. And in cystic fibrosis, as you've heard, CF cells tend to be directional and tends to go to the top layer or the apical membrane where it performs its function. So these all provide different areas where things could go wrong and potential areas where things could be addressed. Now, Dr. Sazne went into some detail in these mutation classes, which I'm very grateful for. And as he mentioned, these class 1, 2, and 3 mutations are typically, although not always, associated with the need to take pancreatic enzymes and also some other complications of CF you see listed on the right-hand side, generally in the GI tract. Whereas the class 4 and 5 mutations are not associated with, generally not associated with pancreatic problems, although they could be associated with pancreatic inflammation. And as he emphasized very importantly, a lack of good correlation between the class of mutation and the prediction of lung function over time. So how can this be used therapeutically? Well, the approach to treating the CF problem by correcting the function of the protein, the term that people are using for that is modulation. So a modulator would be basically any drug that will restore function rather than replace the protein or replace the gene. So the important part of that, it addresses the primary cause of CF. It really attacks the root of the problem. But based on this manufacturing process that involves these different stages, there are different defects and different targets and different strategies. So for example, the class 1 defects generally are focused on the fact that a protein is not made properly because of a problem in translation. A class 2 defect is a clinical problem because the protein that is being made doesn't look right, doesn't act right. And a class 3 problem is a protein that looks and generally acts right, but is not regulated properly and doesn't function properly as a result. So there is a rough correlation between where these problems occur in the manufacturing process and what we recognize as these classes of mutations, and that does have incredibly important implications for therapy. So let's go into some of the details about this and start with the class 1 defects. So remember, this is the type of defect where normally you have translation from DNA into protein by using this RNA in the portion of the cell called the endoplasmic reticulum and a little organelle inside there called the ribosome. And normally, the messenger RNA is read as the ribosome moves along and adds amino acids so the protein gets built up. In normal biology, you get to a point where you have to stop. So there's a message in the DNA that says, stop now, you're finished. And as a result of that, you then have a full-length normal protein made. That's the normal way our cells function to make proteins. A stop mutation, which is this class 1, has a genetic change that gives a false signal to stop before it's really time to stop. So that's called a premature termination codon. You can think of it as a stoplight that's put in the middle of the highway. And the result of that is that you don't have a normal protein made. You have a truncated protein or no protein if it happens very early in the process. And that's the problem with people with class 1 mutations. So is there a way to address this? Well, it turns out that there are small molecules that can bind to the ribosome and actually help it to overcome the stop signal that is abnormal. So it bypasses that stoplight and goes on to the normal end process. It actually recognizes the normal stoplight, and as a result, you get a full length of protein. It sounds almost like science fiction that we're able to do this, but there are, through the discovery process, ways to do this. And this drug called PTC-124 is the first drug that's been available for clinical trials that works this way, that specifically addresses the problem in CF and also other diseases that have stop mutations. Now, it turns out some antibiotics can do this also, like gentamicin, but the doses that we would need to give would be toxic. It's not really usable as a therapy, but it did actually point the way early on in this area. So in the early experiments using PTC-124, what was noticed in cells was that in CF epithelial cells, on the left-hand side, you see the fact that there's a kind of dull green hue to the cell outside the red nucleus. And that's because an antibody against CFTR is not really lighting up anything. It's not being made. So that's a stop mutation. But when you give that cell, when you sort of bathe it in this drug, you see on the right-hand side that suddenly we have the CFTR visible where it's supposed to be on the apical surface of the cell. How is this looked at in clinical trials? Well, in the development program for PTC-124, which is now called Ataluren, the most important test that's been relied upon has been the nasal potential difference. And Dr. Sosnay mentioned this briefly. Some of you probably had this test done. It really is a three-part test. We notice that there are differences between people with CF and people who are healthy. People with CF have a more negative electrical charge in their nose because of the dysfunction of CFTR. So that's called a higher basal or baseline nasal potential difference. So in the test, first that's measured, and then a drug is added directly into the nose called miloride, and what this does is block the sodium channel, and that causes a fall in the nasal potential difference towards normal, which you notice is much greater in people with CF than in healthy people. So that's the second noticeable difference you can see. Then after that, some changes are made in the solution, and a stimulus to CFTR protein itself is given, usually something like isoproterenol. And in a normal situation, there's an opening of that chloride channel, and the nasal potential difference becomes more negative again. But in cystic fibrosis, there's no response. So that's the full tracing of the nasal potential difference. And it turns out that in clinical work, you can look at each of these components, and people will focus on different things. But in the PTC-124 trials, what people have tended to focus on is the direct function of chloride secretion, which is that last part of the nasal potential difference. So this is an example of a clinical trial. You can see the numbers of patients treated at the top there. And the first two areas show two different dosage levels that were given. These are 3 doses a day of different doses. And they're treated for up to 112 days. And on the right-hand side, they've combined all the information at both dosage levels. And what you see there is as the trial proceeded from day 0 to day 112, there was a gradual move towards normalization of the nasal potential difference. And then if after the end of the trial, when the drug stopped being given and they were measured again later, things returned back to where they were beforehand. So this is some indication that this drug, ataluren, may be a way to treat these stop mutations. Another part of this trial looked at some clinical readouts because, as interesting as nasal potential differences are to look at, what does it really do for the lung health? And that's what we're really interested in. And in this same trial, what we saw here were trends. These were not significant, but the numbers of patients are pretty small in this trial. Trends towards improvement in lung function, and also an improvement which was statistically significant in reducing of the amount of coughing. And the cough was actually measured with a device. And those of you that have been involved in the ataluren trials know about the LifeShirt device that measures the coughing. So these are all indications that this is a drug that might work for CF. So where do we stand with this now? Well, a phase 3 or definitive trial of ataluren has now been conducted and finished, and we're actually waiting for the results of this. It could come any time now. We've been expecting them. And so we should know very soon whether or not the drug meets the standard test. Potential problem here is that this was an international trial. It involved patients from the United States, other places in North America, Europe, and also Israel. Why Israel? Well, it turns out that in Ashkenazi or European Jews, stop mutations are the most common cause of CF, unlike here in the States where delta F508 is the major problem. So a lot of patients were enrolled in Israel, and the types of stop mutations vary depending upon the geographic area and the ethnic population. So it may be that there are very subtle differences that will come out, and we don't know yet. But stay tuned, because this could be very important, as stop mutations affect 5 to 10%. In Israel, over 50% of the patients with CF. So this is a very important area, and it's probably not the last drug that's going to address the issue of stop mutations. There are a lot of diseases, a lot of genetic diseases, where some of the cases are caused by stop mutations, things like certain types of muscular dystrophy. So this could have very wide implications in medicine and personalized medicine in the future. And it's a very important template for how to look at this problem. So that is the Class 1 program now. And now I'm going to move to the second area I want to talk about, which is the Class 3 mutations. This is where ivacaftor or Kalydeco comes in. And remember, these are the so-called gating mutations. So the drugs that affect, what is the gating mutation? It's the protein that is where it's supposed to be, but it's not opened and closing properly. So its function is greatly reduced. And that's shown here in this slide in the middle. If you can open that channel more of the time, you increase the function of the channel. G551D happens to be the most common of these types of mutations, and that is why it was selected for clinical trials. It affects about 4 to 5% of patients with CF. How do we know it works? Well, it was based upon work in the lab. On the left-hand side, you see some electrical studies, and what the x-axis or horizontal axis is showing is as you add more of this drug, VX770, to a epithelial cell culture, you increase the chloride secretion or the chloride conductance of that system. So electrically, it's working. And on the right-hand side, you're looking at the actual time that the channel is open. So what this drug is doing, as you can see in the middle dark bar there, from the untreated to the treated cell, it's markedly increasing the time that the CFTR channel is actually open. In fact, it's actually greater in this experiment or set of experiments than in the wild-type cells. So if you or I took ivacaftor, VX770, Kalydeco, we would all have some increased activity of CFTR. It works on all kinds of CFTR if the channel is openable. Patrick Sosney showed you a little bit of the data from the clinical trials. We did this in a number of different stages, and I think most folks are familiar. We had the phase 1, 2, and 3 trials. Phase 1 trials really are looking at safety and tolerance and also how a drug is handled by the body. Then we move to phase 2, where a larger number of patients are looked at, and we start to look at indications of efficacy by looking at biomarkers, which we think have some relationship to clinical benefit, but on a short-term basis. in a relatively small number of patients. So this is the phase 2 study that was published in the New England Journal at the end of 2010. We did it in 2 parts. There was a 2-week section and a 1-month section. And what you're seeing here on this slide are the sweat test results. The blue line represents people that got a placebo. We start out at about a sweat chloride of about 100. Sweat chloride turns out to be a pretty good test. It doesn't have a lot of variability. It doesn't change much. So as you see over time there, that blue line stays pretty much unchanged, and it does so in both parts of the study. But the lines under it represent increasing doses of VX-770. And those sweat chloride results go down. They're down by day 7. In fact, in the second part of the study, they're down by day 3. So this is a rapid effect on the sweat gland. And the really exciting thing about this is the magnitude of the change. If you look at the vertical or y-axis, we're going from levels of 100 initially down to 60 or below. Now, why is 60 important? You may remember that that number is the cutoff for the diagnosis of CF. Most people who take this drug with G551D actually move from the CF into the normal range in their sweat chloride. So that was a very, very exciting result. But does that mean it's really going to be a drug that benefits them clinically? We don't know that, but one indication from this trial that suggested it was that when looking at the NPD, remember we just talked about that for Adalurin, in both the 14 and 28-day studies, there was an improvement in the nasal potential difference in the portion that looks at chloride secretion in patients, and there was a general dose response. So the more of drug you got, the better that result was. So that meant that the drug was not only helping in the sweat gland, which is nice, but maybe not helpful clinically, but it actually was working in the respiratory tract. And finally, I think the most surprising thing to many of us who were involved in this study was that we actually saw a change in lung function. Although the numbers are small, and they're no more than hints, again, there is an improvement in lung function that can be seen by day 14 in both parts of the study in FEV1. And most of us really thought it was going to take longer to produce this effect, but it was really startling that this happened. So based on this very positive result, we went ahead and did a large study with many centers, and we participated in this, that was more recently published a couple months ago, and was the basis for the FDA approving ivacaftor or Kalydeco for use in patients with G551D. So this slide really summarizes all the major results here. And on the upper left-hand side, you see the change in the FEV1 in these patients, and it occurs very quickly, as we noticed before. And the important part of this is that it was sustained for an entire year in the patients that were receiving it. And we now have patients that have gotten an additional year of therapy, so we know it's sustained basically indefinitely. We also see changes in the nasal potential difference in the phase 2, but in the phase 3, what we're looking at here is quality of life in the bottom left, as well as symptoms and weight gain. It's a little hard to read on the laptop here. But the thing about the clinical outcomes that is so exciting is that in addition to the lung function changes that we were hoping to see based on the phase 2 study, we had this very large gain in weight in comparison to patients taking placebo, which meant that somehow the drug is also affecting either appetite or function of the GI tract at some level, whether it's in the pancreas or the small bowel or some other aspect we don't really understand yet. But people who take this drug are hungry, they eat, they gain weight, they feel good. That quality of life measure means that they really notice the difference on the drug. So based on that, the FDA has approved the drug. And finally, the sweat chloride results that were noticed short-term were also sustained over the year, as shown here. And most patients, as I mentioned, are going into the normal range. So is this drug a cure for CF, for patients with gating mutations? That may be going a bit far, but I think it's fair to say this drug controls cystic fibrosis. We don't know if it's going to keep doing it year after year after year, and we just have to wait and see, and we're following all patients who are being prescribed the drug very carefully to see what happens to them. But it really does point the way to the fact that a drug that is aimed at a particular mutation can work and have very dramatic results. Patrick mentioned the fact that there are other gating mutations besides G551D, and there are other mutations that have residual function, these class 4 and class 5 mutations. And a big challenge coming up is going to be to see whether Kalydeco helps those patients. It's a very big practical problem because, as you probably know, the drug is extremely expensive. Insurance companies are most likely not going to reimburse the expense for people that are not on label. There may be arguments even getting people who have G551D access to the drug, and plans have been set up to do that. So we're really just embarking on a whole new era in terms of seeing how far we can go with this medication. But it's possible that we can add a substantial chunk to the 4 to 5% that are now eligible with further studies. I should also mention finally that one of the phase 3 trials that was done with Kalydeco was kids 6 to 11 years of age. So the data I showed you from the New England Journal article really was for people over 12. But in the childhood group, it was also a very good result. The drug improved lung function actually as much or more than it did in older people. And that's really kind of interesting because most kids have pretty good lung function these days. And we still got a huge bump in lung function over the year that the kids were on the drug. And the secondary endpoints also were similar, that the sweat chloride dropped in the same way, and there were also significant weight gains. So this seems to be applicable to children down to school age. Another challenge in looking at this, and somebody raised the issue about newborn screening, is the fact we're going to be picking up babies and kids with this mutation who are obviously 3 months of age or maybe higher. And the question is, can they benefit also? Can we actually prevent the onset of a lot of the secondary complications that we're all familiar with? We don't know the answer to that, and we need to do studies that involve very young children. That's another large piece of the agenda going forward, is to learn how to do studies in babies and very young kids with CF for drugs like Kalydeco. I'm going to finish up with the class 2 mutations. I'm not going to really be talking about therapies for 4 and 5, although except to mention that there will be planned studies of Kalydeco in class 4 and 5 that are going to be getting off the ground this year. Class 2 is the most difficult issue. So remember that CFTR, in 90% of cases worldwide, people have at least one copy of this delta F508 mutation. And it causes a protein folding defect that really limits its function to almost zero. Very little is present at the cell surface. Where is this mutation? This shows its location in this very complex protein. What does it actually do? Why does it cause a problem? Well, it seems that as the delta F508 version of CFTR is being made in the endoplasmic reticulum, the place where that manufacturing translation process occurs, it's recognized to be defective, and it is tagged for quality control being thrown out. So it never gets out to the plasma membrane. You can see that here in this picture where the wild type on the left in green is shown at the top of the cell, but the delta F protein is stuck near the nucleus. So the green kind of surrounds that blue nucleus there where the endoplasmic reticulum is, and none of it, essentially none of it, is present on the cell surface. Now, there's a lot of research going on now about how this problem occurs. And unfortunately, it seems to be a very complex problem. And this is an attempt by one of the main research groups doing this sort of work to explain the problem. And the way I would summarize it is to say that there's at least a two-hit issue here. The first is that within the actual area where this mutation occurs, the so-called MBD1, nucleotide binding domain 1, there is a problem with how this little section of CFTR folds up because of the delta F mutation. Unfortunately, that's not the only problem. There's also a secondary step where normally this part of CFTR also interacts with another part of CFTR, which is one of the sections that goes through the cell membrane. And that double-step process is what really results in the proper folding and packaging of normal CFTR. If you correct the problem in the immediate neighborhood of the defect, you can get partial recovery of function, but you don't get full recovery of function. And if you correct the part of the defect that involves the interaction between this section of the protein with another section of the protein, you also get a partial correction. Only when you correct both things together do you get full correction. So that, to me, says that it may not be possible to do this with one small molecule. We may need to use two or more, but we don't know that yet. And the critical question that Patrick Sosne raised, how much is enough, is a question we have not yet answered. So what do the clinical trials tell us? Well, CFTR correctors are supposed to improve the amount of CFTR that we can get out of the endoplasmic reticulum to the cell membrane, where it has a chance to work. And the compound, the lead compound that Vertex has been working with is called VX-809. And again, the clinical trials have been based on work in cell cultures, which are illustrated here. On the left-hand side, what you see here is that as you increase the concentration of this drug, you get an improvement in the amount of mature or fully formed CFTR protein, which is shown up here in these tracings. This higher band represents the fully mature protein. So there is evidence that this drug can improve the production of CFTR, and also on the right-hand side improve the chloride secretion as the amount of drug is improved up to a certain point. There is a maximally useful concentration, which turns out to be achievable clinically. So the first study that we did with this was to look at the effect on sweat chloride in people who have 2 copies of delta F508. And that was recently published. And you can see here, looking at the sweat chloride, the placebo line is the black line with the open circles. And as you would expect, it basically stays unchanged throughout the 1-month trial. But certain concentrations, all except the lowest concentration, actually showed some improvement in the sweat chloride during the time of the trial, beginning at day 7 and being sustained through the 1 month, going back to baseline after the drug stopped being administered. Now, thinking back to the result for Kalydeco, you can see if you look at the vertical or y-axis that there's a big difference in the magnitude of this effect. Instead of going down 50 or 60, we're going down 5 to 10. So it's a small effect, but it is significant. And it really represents a proof of principle. Now, is that enough of an effect to cause a clinical benefit? Patients in this trial had no change in their lung function or other measures of clinical disease, so we think not. And that would go along with this relatively small change in sweat chloride. This is also summarized here as a mean, and you can see that there is basically a dose response. The more VX-809 you give, the better effect you get, but the magnitude of the effect is small. So based on the fact that at least up to a certain dosage of 200 milligrams, the VX-809 produced a change in sweat chloride, which is sort of proof of principle that you could get an effect, but the magnitude was small. The next level of thinking was to try and combine this with Kalydeco, or VX-770. So the thinking here is shown, is schematized here. The corrector, VX-809, correcting this folding defect, would allow more of this protein to get to the cell surface. And then the VX-770, remember I said it would work basically on any CFTR that's present there that can be opened and closed. It actually does improve that. And there's experimental data that supports that in tissue culture, which you see on the right-hand side here. You can see the VX-809 itself produces a slight increase in chloride channel activity. 770 also produces some effect, but when you give them together, you get 3 different doses that are shown here. You get at least an additive, if not a synergistic improvement. So that led to the idea that perhaps we could combine these 2 drugs together and maximize our chances to improve the situation. So a trial was started in which we gave a combination of VX-809 and ivacaftor, or VX-770, Kalydeco, to patients. And the way this was designed was to have 3 arms. One was a placebo arm, which is called arm 3 there. But the first 2 arms, what they did was to give a single dosage level of VX-809, 200 milligrams. And in one arm, one dosage of either Caftor or Kalydeco, and in the second arm, a higher dosage. The first 2 weeks, just the 809 was given alone as a kind of baseline. And then for 1 week, patients got the two drugs together. And the main readout of this was, again, looking at a biomarker, the sweat chloride test. And what you see here is that the combined effect of 809 alone was about a 4 millimole change in sweat chloride. That is like 100 down to about 96 or 95. Pretty modest change. But when you added the higher dose of Kalydeco, of 250 milligrams, you got another 10 millimole change or so. So the total change together was about between 10 and 15. Now we're starting to talk business here, because we may be able to move that number further by giving longer time exposures and higher doses. And that's what we're doing right now. So this is a trial that's ongoing in a new part where we're giving these two drugs together for a much longer period of time and using higher doses of VX-809. We hope to have the results of this within the next few months. We've finished enrollment for this particular phase of the trial, so we should have results within that time period. And that'll really give us some indication as to whether this is a path we can continue down. And we'll have to look at the amount of sweat chloride change, but also whether there are other changes that suggest it's really helping folks with CF, namely improved lung function, weight gain, things like that we've seen with Kalydeco in the G551D group. So what if it doesn't work? Well, Vertex has another compound called VX-661, which is also now in clinical trials, early clinical trials, which may function better than 809. We don't know that, but it's possible. And as I mentioned, if you think back to that assembly diagram, there are other ways to think about correction in CF where we give actually more than one corrector, maybe combine two correctors or even use two correctors with a potentiator. So I want to leave you with the idea that this is the beginning of a long journey in terms of the 90% of patients with delta F508. And we're going to get there. And we're moving pretty rapidly, but you have to at least let the process go step by step. Participation in the trials is really important. We really appreciate all the folks that have helped out. Thank you. Any time for questions? Or? All is clear?
You talked about there being two issues with 508 as far as folding. Which one is 809 correct? Is it the nucleotide binding domain, or is it the other association with the other portion of the FTR?
I don't know. This whole business about where these drugs are actually acting and what they're doing is not well understood. And I think there's a huge amount of research that needs to be done. Part of the problem is that the structure of CFTR itself has not been fully identified. There's a process called crystallization, which you really need to understand the full three-dimensional layout. We still don't have that for the whole protein.
Thank you, Rick. That was great. We're all going to hang out for the whole day, so if there are questions, please take the opportunity of the different breaks, and during lunchtime, that would be perfect to have more one-on-one type of discussions of your questions. Our time is fairly tight, unfortunately, and I would like Meg and Lindsay to come and briefly update us on the support groups that we have for patients and families.
Yeah, I think you're first.
Which one?
Right here.
This one?
Yeah.
Mm-hmm.
Yeah. I'll just press this one. I think so. Okay.
Good morning. Everybody hear me? Can you see that? I'm Meg Dvorak. I am the adult CF social worker, and I just wanted to talk a few minutes about my support group. As many of you know, I've had a support group going for a little bit over a year, and since its inception in January 2011, the group has really evolved, and I've been able to add a WebEx and teleconference component to the group. I added an extra half hour onto the duration of the group because we found that month after month, the CF patients would stay for an hour after group talking in the hallway because they just didn't get enough time in the group, and there was a lot more to say. So that's another added feature. And also the group has just developed its own sort of steady following of patients month after month, and we have others that join us and then can't join us, but we always have like a good critical mass of patients. And the group has evolved into a really unique and powerful therapeutic tool, something that I don't think is available for the patients on Facebook, CF chat rooms, or even in private therapy. So I want to encourage everyone who hasn't tried the group to give it a try and see how you like it. In your bags that you got today, everybody should have a flyer for the group. It's got two sides on it, and on the back it's got a map of the group's location. And here's some details about the group. If you don't already know, we meet once a month on the first Friday of the month from 11:30 in the morning until 1. Unfortunately, I'm not able to serve food at the group. I wish that I could, but there's many reasons why I can't. The group meets at the LKS Center, which is right next to the medical center. It's a really short walk, just kind of jog to the right from the adult hospital. And within that building, the room location of the group actually changes from month to month because it varies depending on what's going on at the medical school. So the best way to really find out about where the group is, what the topic is to get on my email distribution list. And I want to let you know I have a sign-up sheet just outside on the table. So just put your name on the sign-up sheet and your email, and I'll just add you to my monthly list. And what I do is I'll send out an email the week before group. The email contains the topic for that month and the specific room location and any other sort of changes or updates. So you can also email me if you want. My email's on the group flyer, which is in everybody's bag, and just email me and say, I'd like to get on your distribution list. The group is mostly targeted to CF adults, and the conversation and the content in the group is very therapeutic in nature. So it allows CF patients to share their feelings, their thoughts, all their experiences, anything and everything CF and beyond in a very confidential forum. The topic changes, and it's always a topic that's sort of relevant to CF. I've covered everything from pre-PFT anxiety to nutritional needs and psychosocial issues around eating and diet. I've covered anxiety, stress, lung transplant, anything. So if you have ideas about topics that you'd like me to cover, I'm happy for all that kind of feedback. And, you know, I can talk to you all I want about the group because I love it, but this is some patient feedback that I've gotten. And you can probably read that a lot faster than I can say it. But just want everybody to try the group out. I think you'll like it. Any questions? Yes?
Do you offer anything after work hours?
I wish that I could, but just room availability and my own schedule and the way when our clinic meets has made that difficult. I'm open to maybe looking at that in the future, but for now it does happen midday. The one thing that I think is a benefit, I mean, just given that safety in this community is my priority. So unfortunately, I can't allow people with MRSA, B. cepacia, or multi-resistant bugs to attend group. However, they can call in, they can come in on the web, and all those instructions are sent out in my monthly email. Also, there's geographical barriers. Maybe somebody comes to our center, but they're from Reading or they're from, you know, way down south. They can come in on the internet or they can call in and teleconference into the group. I'm able to capture a lot of patients that way. In fact, sometimes the virtual attendance in group is higher than the actual physical attendance. Questions about that? Okay.
Hi, I'm Lindsay, the PEDS social worker. And a year ago, I said that we were going to start a support group for newborns. And between maternity leave and relief social workers, it didn't quite happen. So the goal is to start it the first Monday in April. It will meet monthly, the first Monday from 12 to 1. It'll be at the 7:30 conference room. And it's mainly geared towards the new diagnoses, so ages between 1 week to 3 years old. When we kind of met to discuss what ages would be, how we were going to do this to split it up between ages and parents and everything, it seemed like the biggest need at this moment, and some of the families that were raising the biggest concerns, were more in our newborn population. And so we felt like this was going to be a good start. And my goal is to work with Meg to eventually get it on WebEx and how Meg is doing, because I have been to her support group, which has been really successful. And we figured that the first Monday would be great because that is our newborn screening clinic. So the families that come can just come straight into, obviously, if you have your child, we can't have you in the room with your child, but that we would encourage parents to be able to come to this support group. And I understand, just like Meg said, that the timing isn't, it's not the best time. We can't figure out a time that's going to capture every single family's needs, but we'll do the best we can, and as we see how things go, we can kind of make changes. And I'm working with the parent advisory group to kind of see what their thoughts are, needs are, and everything to kind of move forward. So in your guys' bags is also a flyer for the support group, and the plan is to try and do half of it as a support group and then half of it as having people like Julie come in and talk about nutrition, or Kristen come in kind of talk about some RT things, or Mary to kind of come in and talk about some of the educational needs in terms of CF. So we want to cater to whatever your guys' needs are as parents, but I really feel like this would be a good way, especially for new parents, to get to meet some of the other parents that are at our center that have seen and have gone through some of the things that you will go through in the future. So if you have any questions, I'll be around today, and just let me know.
Grab their coffee and find a seat. I'll make a few announcements. I'm Carlos Mila. If you don't know me, I'm the Center Director now at Stanford, and welcome to our CF Education Day. It's our 12th annual CF Education Day. Thanks to all of the team at Stanford. We had very successful meeting year by year.